Thanks. Yes, so black hole mass versus the age of the universe. And so we expect at early times the metallicity to be lower and here higher. And why do we expect black hole masses, the maximum black hole mass, to be higher here than here? It's because we expect the mass loss to increase with metallicity. So basically, the talks of what is the mass loss rate as a function of metallicity, or what is the black hole mass as a function of metallicity, are basically the same talk. It's just the inverse. So, most of the work that I will discuss actually by my PhD student Ethan Winch, and I'll get to that. But let me first get to the Hertzsprung-Russell diagram. Thankfully, Tom already showed one, because for a moment I thought, has no one shown a Hertzsprung-Russell diagram yet? It can't be. So basically, oh yay, that is me. No. Well, in that case, I'll just do it this way. So if you have a 60 solar mass O star, you lose a lot of mass, you become a luminous blue variable, lose a lot of mass because stars cannot be over the Somfix-David limit, and then you strip the star and become a classical Wolf-Rayet star. That is the Conti scenario. When you go down and down in mass, at some point the winds are not strong enough for that to work. So in that case, maybe a 20 solar mass star makes a red supergiant and explodes as a type 2. That is the bit that, well, until yesterday I thought we understood. But all this we don't understand, and there will be a combination of binary interactions and wind mass loss that will cause the existence of these stripped stars. And people sometimes say there's a pendulum. In the 60s, everybody thought these come from binary interaction. Then winds were invented, and it's all from winds, and then it goes back to binaries and winds. I don't think that's true. I think the only pendulum is where, above which mass does the Conti scenario work. There will be a mass where, above which the winds are strong enough that it works, and there will be a mass below which it won't work. And the only question is, where is that critical mass? So that is basically what I want to emphasize here. So I just talk about single stars, and I'm agnostic about whether gravitational wave events or other events come from binary interaction or cluster events. I just look at the building blocks of the single stars. So, as I said, the wind mass loss as a function of metallicity is the first part of the talk, and then the black hole mass function, and I make assumptions, obviously, because I don't follow the full evolution until the very end, and definitely not the final part. But let's look at some motivation of why this is interesting. So, there was this first gravitational wave event, now a decade ago, and this is the physical interpretation of this, and the maximum black hole mass versus metallicity, solar type, very low metallicity, and the claim was that you needed weak winds. As you see, at solar metallicity, actually, these two curves are both at the same point. So it has nothing to do with that the winds became weaker. But what really is the issue is that this plot, basically, from a population synthesis with Chris Belzinski, is the exact same plot, but now with the correct labels. Basically, in the population synthesis with Hurley, there was no Wolf-Rayet mass loss metallicity dependence, so it didn't matter whether you were in the Milky Way or low metallicity, the maximum black hole mass was only 10 or 20. And if you include a Wolf-Rayet mass loss metallicity dependence, then you can go, let's say a tenth or so, you can go into this regime of the 40 or 30 solar mass black holes. So it is useful, because these kind of things have been included in basically all the population synthesis codes, to look a little bit under the bonnet of what are the assumptions about the winds that go into these codes. So what's really happening is that we have this, and now the metallicity is on this axis, so sorry, the solar case is here. So at lower metallicity, the mass loss rates come down, whereas the idea was, before that they were always the same, because there was self-enrichment in Wolf-Rayet winds, that carbon, nitrogen, and oxygen were producing the metallicity-dependent winds. What I actually found is that CNO only take over very low metallicity. But in most of the universe, there's a strong iron dependence. So in our earlier model, you're slightly increasing Yes, that is because the O star mass of metallicity dependence was already included. So iron is very complex. That's why there's millions and millions of lines, and therefore there's so many transitions that you can have a high mass loss rate. Where CNO are a bit more like hydrogen. So that is why iron is really the key to driving these winds. I don't have time to go into the whole theory of line-driven winds. Just want to say you have photons that accelerate atoms, and you get mass loss rates as a function of basic stellar parameters. What you definitely need is a luminosity. More photons, higher the mass loss. The mass is important. Often people say higher mass stars have higher mass loss rates. That's wrong. For the same luminosity, of course, it's the other way around, because it's harder to overcome the potential well if you have a higher mass star. So the mass rate goes down. Metallicity and temperature. So it's not just a function of Z. You need to know the right L and the right M dependence. And that is the gamma dependence, and I'll come to that. In reality, that's a multiple scattering process, and we have many photon interactions, and we can get in the wind, we can have a momentum per second, m dot v infinity, that crosses the momentum in the radiation field L over C. So the efficiency can be larger than 1. Eta can be larger than 1. And there are other methods of including the same physics with common frame codes. Normally, these kind of codes, like fast wind and CMF-gen and power, have been used to get empirical mass loss rates based on line emissions, but you can also use them to directly integrate the radiative acceleration and come up with hydrodynamically consistent mass loss rates. Also relevant for this talk is what is a very massive star. So those are stars above 100 solar masses. Sometimes people think that very massive stars are over 10,000. I would call them supermassive stars. But I would say both very massive stars in the 100,000 solar mass range and the supermassive stars will be characterized by very high gamma. L over M ratios are extremely high, and you really need to know the opacity to see what the mass loss rates are. So that is very different from a 10 solar mass star. In a 10 solar mass star, you're far from the Eddington limit. These stars are very close to the Eddington limit. That makes them very different in their physics. And what happens, if you plot the mass loss rate plus this gamma factor, for the normal mass 10 solar mass O-type stars, you have a Custer-Emerton-Klein type gamma dependence, where mass loss rate goes with gamma to the power 2 or so. But then above this transition point, this red dot, we find a much steeper dependence. We find this with Monte Carlo, and we find it also analytically. And at this red dot, you can show analytically that the wind efficiency number that I just showed, the m dot v infinity over L over C, crosses unity, where the winds become optically thick. So these stars are O-star winds, and these stars are a type of Wolf-Rayet stars. Not the classical Wolf-Rayet stars, but hydrogen-rich Wolf-Rayet stars. And if you don't include this boosted mass loss rate, and you just have the blue dot, you severely underestimate your mass loss rate. So in the regime where mass loss is extremely important, you're underestimating it, if you don't take that into account. So what we really have for an O-star, you have absorption lines, like in the sun. For these very massive stars, you have these emission lines, tau larger than 1, and in between with this more p-cycling type behavior, these are slash stars, OF slash WN, where this is crossed. And that is really interesting, because you have this eta equals tau equals 1, you can write down the mass loss rate straight away. Let me just make that very, very clear. So eta is m dot v infinity L over C. So if eta equals tau equals 1, then the m dot, sorry, let me just say it here, m dot is the luminosity v infinity C. C is a constant, very simple. V infinity can be measured. So if you know you have a transition type star, the mass loss rate is no longer dependent on clumping or all the uncertainties in stellar winds, it's only a luminosity determination. And that is extremely important to anchor mass loss recipes. Very massive stars are seen in young clusters like R1v6. You have the helium-2 emission line, the 7 very massive stars that produce all of this. Normal O stars don't do that. So when you see these features, you know you're looking at very massive stars. And they may well be very prevalent at high redshift. This is no longer just a kink from Monte Carlo. We use power code with the implementations of Andreas Sander. And what we find, the same behavior, Maslow's rate versus gamma, we get a kink in the Maslow's rate, and we cross tau equals 1 at the kink position. So we have new Maslow's rates coming up with these more sophisticated codes, but the same basic physics and the same anchoring of Maslow's rates. So if you ask me the question, which Maslow's rate should I use? What should I put in my population synthesis code? People will tell you, oh, you need to use a theoretical Maslow's rate. And other people say, no, you need to use an empirical Maslow's rate. I need a glass of water. Now there's many different ones, of course, but these are the two most used, I think. So that's why I put them. One thing to look at is what are the dependencies. In this one, for instance, there's only an L and a T effective, so that's quite limited. You really need the M dependence, I think. But it's also not the case. Sometimes people think empirical should be more trustworthy because that's observational. Well, that's not the case, because we get empirical Maslow's rates by using the same model atmospheres, but now with clumping included, which makes it more uncertain. So often, the empirical rates might give you differences from the theory, but we don't know which one is correct. Because they're both theoretical. And they both make assumptions about clumping. Because it's all time independent so far. In reality, things are not stationary, and we have a lot of work ahead of us. Now, what we need to test the theory is still to get empirical Maslow's rates, so that we can get these kind of recipes. But for that, you don't need just Maslow's properties, you also need the stellar properties. Because you can only compare two Maslow's rates if you have the right stellar parameters. And that is not trivial, because the mass is not so easy to find always. The best way to do this is to combine optical and UV, and that is where we come with the project that we're doing with Hubble and with X-Shooter, called X-Shoot-U. And what we really want to do is get V infinity from the UV, temperatures and gravities from the optical, and then H alpha gives you a good idea about mass loss, and by combining the B-Sydney lines in the ultraviolet and the H alpha lines, we get a handle on the clumping, and we should be able to get better mass loss rates. Because this is now a homogeneous survey with hundreds of stars, and in the LMC and the SMC. So that looks like a lot, hundreds of stars, but still, you need many parameters you need. Luminosity, mass, temperature, metallicity. So these are, yeah, we still like larger samples. But we're getting to interesting results. I don't have time to look at all the early results, but watch the space for the final answers. Yeah? So, what recipe should you use? As I said, this is absolutely critical, that your Maslow's recipe crosses that point. If it crosses that point, and my recipe from 2001 goes right through it, that means it could be correct, but it really only means it is correct at that point, right? It can still be overestimating at lower masses and underestimating at higher masses. That's the impression I think most people would have, that at, say, 20 solar masses, the Maslow's rates from this recipe would be too high. We enter a weak wind regime, and for very massive stars, it's probably too low. We need a steeper L over M dependence. So, that is for hot stars. What about red supergiants? People, of course, have been working on red supergiants for a long time, and I don't know anything about red supergiants, so forgive me for saying something that will be offensive. But if I see a plot of data, the Maslow's rate versus L, of red supergiant data, yeah, and I see a kink, quite clearly, very similar to the theoretical kink in hot star winds. Now, both winds are thought to be partly driven by radiation pressure. So, what if, just because we have a different opacity here, no longer atomic gas opacity, but molecular and dust opacity, it could still be the case that this is caused by the same physics, a gamma-dependent wind. And that means an inverse M dependence. So, if you have that, you have a relatively low Maslow's rate for the bulk of your red supergiants, but when the stars evolve up and up the luminosity range, and the mass keeps going down, because of mass loss, you can get a runaway. And I think this physics can be relevant for not just red supergiants, but any supergiant. Okay, that was part one. about the mass loss. Now, the question about the final product. We have now implemented this kink in MESA, and for very massive stars, 500, 400, 300, 200, you see very interesting behavior. Stars no longer go to the right, but they go down. You get a vertical downwards evolution during the hydrogen burning main sequence. From the very start of hydrogen burning, you go down, then you make classical Wolf-Rayet stars, and you have a second vertical evolution because of, again, classical Wolf-Rayet stars that also depend on gamma, and that means that your stars evaporate. So at high metallicity, if you observe stars between 1 and 2 million years, like in R136 of 150 solar masses or so, it is now very hard to tell whether that initial mass is 200 or 1,000. Just from this behavior, you cannot tell. Potentially, the hydrogen-helium abundance can teach you something to constrain this. But at the moment, it's very hard to tell. That's interesting, though, because if you now look at the black hole mass function, and I say black hole, but it's really the final mass of our models, at the end of core carbon burning or so, masses versus initial masses. Now, it is definitely not the case that, that this thing keeps going up. What we see is that for very massive stars, we have very low final masses. And then you have a peak at about 30 solar masses, but that peak is reached already at 40 solar masses because of this gamma-dependent mass loss, this optically thick transition. And interestingly, when we plot the times mass, so this is the end of core hydrogen burning, you have the exact same behavior, just shifted to higher masses. So that means that a lot of the black hole mass function in terms of this maximum is already imprinted by the end of core hydrogen burning. Sorry? It's solar metallicity. This is solar metallicity. Yeah. By the way, this kind of peak has also been seen in Bavera et al. But there it was also about 30 solar masses, but at much higher initial mass, like 70 or 80. But this was not included in that, of course. Okay. Now we go to low metallicity. This was really spurred by this event. Very interesting. That was an 85 solar mass black hole, right in the middle of the parent stability gap. So the original gap was between 50 and 120, assuming the stars have lost all their hydrogen. And this object had something right in between that. So all kinds of potential scenarios, and I'm not denying any of those possibilities. I'm just saying, is there, purely from the wind physics and the stellar evolution, a possibility to make such an object? It's an interesting question, independent of that particular gravitational wave event. So how do you make an 85 solar mass black hole? From a single star? Well, you have to at least start with 85. Right? I think we can all agree with that. Yeah? And it can't, actually, it can't be too massive either, because the critical CO core mass has to stay below 36, because if you go above 36, you go parent stable. Now, if you have too massive a star, if you go above 100, the core becomes bigger and bigger. You're already crossing that limit very easily. And if you go to 200 solar masses or so, then you have a completely chemically homogeneous star because of the whole star is convective. Yeah? So there's a limited mass range where you can do this. You need to keep your, what we call alpha overshooting, relatively low. There's a lot of uncertainty about this, and I'm not even actually talking about overshooting here. I'm just saying, from observations, there are different core sizes. And people can say you have a low overshooting or a high overshooting. And so the seismology doesn't tell you what overshooting is, it just gives you a core size. But it has to be relatively low, and also your rotation rate has to be relatively low. You can't have too high rotation either, because then your core grows as well. So we have a mass regime between about 185 where you could do this. And then that means, to make 85, and you have 36 maximum for a core, you need a huge hydrogen envelope, and you can do that to go to low metallicity. So those are the criteria that you need to make such an object in the parent stability gap. Can we do that? Yes. That can be achieved. Blue supergiants can do this. So here we have a model of a blue supergiant at MESA, and the advantage of this being a blue supergiant is that it's not as huge as a red supergiant. So we have a potential that this envelope actually falls onto the black hole. Now, I was a little bit confident until yesterday, but maybe it needs to be proven what happens in the final phases if something like that can actually end up in a black hole. But we wanted to do this more extensively to really test all the different parameters. So we have the critical core mass experiments here, where we checked what is the critical core mass in our models. And the CO core mass is 36. That corresponds to a helium core mass of 40. Yeah. So if we now vary all the different mixing parameters, like the alpha overshooting or the omega or the LT semi-convection, you get very interesting behaviors. The alpha semi-convection is totally irrelevant in our mass regime, but the overshooting or the size of the core that we have assumed for the mixing is important, and the omega is important. But it's actually up to about an omega of 0.3 or so. It doesn't really matter. It's only if you're higher than that where you really start to lose the possibility to go to 85 solar masses. And for alpha overshooting, as long as you're at 0.1, 0.2, 0.3, you're still above 80 solar masses. But if you go to 0.5 or so, then you start to reach possibilities that you're no longer populating the gap. But in principle, these models can easily populate the gap. And therefore, when we plot the maximum black hole mass as a function of metallicity, we can have this picture where in the traditional way you would have a maximum at 50, but we have raised this now to about 93. And that is real limit, because you can't go above it, because you can't have negative overshooting or negative omega. Right? So that's a real limit. And then at high metallicity, because of the stellar winds, you go to about 20 solar masses or so. And at about a tenth, you have this transition where the maximum black hole mass drops very rapidly. Okay, that was for omega values up to 0.4. But what about high rotation? Some population of stars might be even more rapidly rotating, especially at low metallicity. You have the possibility to get higher rotation than 0.4. And so far in MESA, people have included Fenton Abbott 86, which is introduced by Norbert in the Bond code and also in MESA. And that mass loss enhancement for rotation is probably valid in the relatively low mass regime, 20, 30 solar masses. But if you go closer and closer to the Eddington limit, then polar brightening becomes important, and it's better to use the omega gamma limit of mid-air. So we've implemented that, and when I say we, I mean Gautam Sabahit has implemented that. And we've also included mass loss because of reaching critical rotation. At solar metallicity, you never reach critical. But at very low metallicity, you already reach it at 0.2 omega. So it is quite relevant to think about what to do at critical rotation. Obviously, this is all approximations in 1D, but this is the best we can do so far. We wanted to see what happens in our models at higher rotation. And this is what we found. So this is what we already did in the earlier paper, and this is what we did in a more recent paper. So what are the red ones here are the final. It's the critical CO core mass, the red ones here, there's a 36. The helium critical core mass, and then the initial masses are here in black, and the final masses in green. So, say for the high metallicity, because we have now this extra mass loss because of the mid-air boost and the critical rotation, you really drop. If you start with a 120 solar mass star, you really drop very quickly to this 40 solar mass critical helium core mass, like that. Whereas at the low metallicities, the low rotations, you see that these two follow each other much better, because at low metallicity the mass is not so high, so the initial and the final mass are almost the same. So what would happen if you put that in a population synthesis? Well, for different omegas, as you can see, you now start to create a pileup because of the mass loss here. You create a pileup because of rapid rotation at about 36 solar masses, the critical CO core mass. And interestingly, there might be a pileup of masses in the gravitational wave data. Now, I don't know if that's a coincidence or if that is really a fundamental feature that is really there. So I'm very interested to know from people if that's a real feature or not. Okay, so to summarize that, at solar metallicity, the maximum black hole mass in our models is 30 solar masses. But that rises to 90 below the parent stability at low metallicity. Yes. So that doesn't mean that other events, other models couldn't explain the 85 solar mass black hole, But I think those are much more exotic than this. This is the most straightforward, I think, way of looking at how to get the high mass tail in the LIGO data. And rotation lowers this, and there is maybe this feature, but there's a quite clear pileup in our models because of the rapid rotation enhancement. And I summarized these points in a recent archive. Okay, that's more or less it. Thank you.
Okay, thank you, Jorick. Plenty of time for questions. Okay, let's start from a little bit back, from Vink.
Hi, thank you for the nice talk. I have too many questions, so I guess I have to pick. So I'm going to go for the last one, the 30 solar mass. Could you go back a few slides to, so here, so the pileup at 35, is that happening here, or that lowest kind of red line is where the black holes will form, right?
No, this is just the CO critical core mass. The point is that there's the mapping from the initial mass to the final mass in green, and here's the final mass, this green one. Mm-hmm. So at lower rotation rates, at low metallicity, you don't lose that much mass. At high rotation rates, you lose a lot of mass.
So which line will form the black hole mass, just for me to understand?
Oh, it's the critical CO core mass, yeah.
So it is a zero. So then, is it the fact that it is always at that same kind of mass? Is that also a consequence
always
of
around this mass?
Yeah.
There's a fundamental limit at about 36 solar masses. Yeah.
Does that kind of really coincides with the switch between core collapse and going pair pulsations?
Yes, that is exactly what that is. This
okay.
These tests we did here. Mm-hmm. And here this is the critical core mass experiments.
Yeah.
Where basically, independent of your input parameters, what initial mass you start with metallicity, you always get the same critical core mass.
Yeah.
But it will correspond to different initial masses, depending on the mixing parameters.
Okay. But so then, in a sense,
that is what is seen in this plot.
I understand better now. Okay. But then, in a sense, the pileup that you're probing is kind of tied to the switch between where pair pulsations would onset and where they would not.
Yeah, that gives you the number.
Okay.
And then it's the rapid rotation and the mass loss leading to the pileup that actually produces that feature.
Okay, thank you. I have more questions, but I'll...
So in the first part of your talk, which was an excellent talk, thank you so much, you mentioned that for normal massive stars, the mass loss rates are a function of 4 parameters, metallicity, luminosity, mass, and temperature. And I was wondering, what about the helium composition at the surface? So I'm thinking in particular, what happens if I have, for example, a star in a binary that loses some mass on the main sequence to the companion, is partially stripped and actually has enhanced helium. Maybe it looks like a WNH star, maybe it doesn't, but would it have enhanced mass loss rates at that point?
So the reason why often people think of helium is because the way recipes have usually included is for an O star mass loss recipe, there was no helium dependence, and in Wolver-A stars, for helium rich, much stronger winds. But helium, if you replace hydrogen by helium, you don't get many more opacity. The number of lines of helium and hydrogen is almost the same. There's no physics producing higher mass loss for helium. The SED changes a bit, so the underlying flux distribution changes a bit, so there's some subtle effects. But the point is, it's not directly the helium that gives you the higher mass loss, it's the indirect effect. You have already lost a lot of mass because you've produced a stripped star. That is why it's so important that you have L and M in it. So if you have a recipe that has the proper L dependence and the proper M dependence, you no longer need the helium dependence. So the fact that often in empirical ways, like Nunes and Lamers for Wolver-A stars, has a helium dependence, is not a direct helium dependence, it's an indirect one. And that is another reason to use theoretical mass rates and not an empirical one.
I have a question about the maximum mass at low metallicity. You put it at like 90 solar masses, right? Roughly, that's what comes out in your last plot. But so do you have thoughts about GW 231123, which has 2 black holes above 90 solar masses now?
Yeah, I have no explanation for that. Not in this picture.
Okay, fine, assuming that it's a real gravitational wave event.
So I'm aware of the object and haven't had time to think about it. But maybe it comes from above. Selma was saying this, but who knows?
Very nice talk. Thanks, Jorick. I wonder whether we can make life a little bit easier, because the dependence on rotation is interesting, which you work out. But isn't it that in the galaxy, as well as now with the Bloom survey, we see in the SMC, the fraction of O stars which is rotating rapidly is small, a few percent at most. And some people think that is even spun up binary products. So to get to 40% of critical rotation, if I understand it right, seems to be a very tall order.
Yeah, I suspect that if you go to lower metallicity than the SMC, then you might get there.
So between galaxy and SMC, there's
I agree. That's the biggest drop. That's the biggest drop there is that we know of in terms of absolute metallicity range. But it's still the case that look, Grace Telford looked at a low metallicity galaxy, and the rotation rates of the 3 stars she looked at, they're all 400 kilometers per second or so, all very high. So who knows? I get your point. But
thank you, Jorick. I wanted to come back to Ilya's question, because I've been looking here at your paper together with Andreas Sander from 2020, when you go through the wind driving from Wolf-Rayet stars, especially W and E, so helium-rich objects. It looks like, if you look at the wind driving acceleration, that helium has a substantial contribution to the acceleration of this wind. Would you care to expand a bit on this?
Okay, I'm not saying that that hydrogen or helium are not important. I'm just saying if you replace hydrogen by helium, I've done these experiments in my 2002 paper. I did not find much difference. I'm not saying there's no difference. The number of electrons changes a bit as well if you have hydrogen and helium.
So it's because there is so much helium that helium has that big role in this case?
Yes, yes.
And the metallicity dependence
But it's not what gives you the high mass rates.
Okay.
It's still the iron.
Okay, and if we would replace this helium with hydrogen, it would have equal contribution?
More or less. Saying. There are some subtle differences, but yeah.
Okay, interesting. Would be happy to talk more about this. Yeah. Thank you.
Sure.
Thank you. Hi. Yeah, so I missed a couple of things here and there, so sorry if this is trivial. I'm thinking about, so I try to verify with LIGO, Virgo, Kaga data that this is the reason why we're getting, an excess of black hole mass at 35 solar masses. Would it help if I can give you a measurements of the mass function from gravitational waves, but now at Z of 2 or 3 or 4? Of course, I'm thinking about what comes after LIGO. Would that help? If this is the reason why I'm getting that peak, what would it happen? Would it disappear? Would it get more peaky? Or you cannot say?
I don't know.
So if I'm thinking about, say, much lower metallicity stars or even POP3 stars, and the black holes they leave behind.
Yeah, if they're low metallicity and they rotate more rapidly, then these facts could be quite relevant, I would imagine.
So you would expect, if this is the reason, that the peak would be more prominent at high redshift?
Yes, I would say so. But also, I would like to know if these events at 35 solar masses, do they have a higher effective spin or not? No?
No.
Okay.
Okay. I mean, it wouldn't be the effective spin. You would want the
it's not the same.
The component spin,
sure.
Which is even harder.
Yeah, I know.
Okay. Is it Like? Or
let me get a couple questions in the back, and I'll come back to you later.
Hi, very nice talk. It's just a quick comment about the helium discussion. Actually, helium-rich atmosphere makes wind driving harder because you have heavier you have a higher mean molecular weight and less free electron in proportion. So it's actually, for a given luminosity, harder to drive a wind for Wolf-Rayet stars, which is why it is important to include, I think, in prescriptions. It's another parameter, but not for the reason of wind driving. It's more for mean molecular weight reasons.
I agree. It plays a role. It's another factor. But it's not in the direction as
In that last bar chart where you were showing the mass distribution, I was wondering the cliff at like 35 solar masses, it seems like there's a peak more like significantly higher, like 20 or something. I was wondering why what mechanism would dampen the merger rate from like lower mass than 35 in this mass distribution.
Are you talking about a peak at 20 solar masses in the gravitational
The
wave?
next slide, yeah.
In my talk? Oh, here. Oh.
Yeah, so it falls off at 35, but
I don't think that's real. I would need to check if this is actually statistically significant, if you have run enough models, or I would need to look at that. I've so far just focused on sort of features at the maximum, because we only do single star evolution, and I suspect to really start doing things like if there is a peak at 20 solar masses, you really need to do the binary evolution. But to learn about whether these features exist at 35 or a tail exists at 80, you can learn a lot from single star.
Okay, thank you.
Okay, me again. Lika, by the way. Sorry, I forget to introduce myself all the time. You showed some interesting HR diagrams of very massive stars that all move down and left. And I kind of have two questions about that. So, first of all, would these all just look like chemically homogeneous evolving stars? Because they never have an envelope, right?
These all look like W and H stars. So in Armagh, they look like W and H stars. So they are W and H. So the H means they're still hydrogen rich.
There is some hydrogen.
They are O star on steroids.
Yeah.
And they have already, because of the CNO cycle, they've enhanced nitrogen.
Yeah.
Yeah. And if you look at a cluster like R1v6, there's 7 of those, and they all have about the same temperature. Yeah? They're all around this temperature.
Yeah, I guess my question was about the hydrogen. Like, is there really still a lot of hydrogen left in these stars at all, or is there a point?
It's about half. Half hydrogen, half helium, by mass, more or less.
The second,
give or take. Yeah.
Second part of this as well is if you go to slightly lower masses, I assume you still kind of go to the left for a large part. So does this explain the the Humphrey-Davidson?
I think this can play a role. This physics can play a role in explaining the Humphrey-Davidson limit. Now, this is at high mass. The Humphrey-Davidson goes down to much lower luminosities.
It doesn't help. Yeah.
But the physics that we include here of becoming optically thick and then having a higher mass loss, an L over M dependent wind, can also play a role for lower mass stars, like LBV type stars, at say 40 or 50 solar masses.
Yeah. And so then do you predict that maybe the high mass end, this is still metallicity dependent, right?
Yes, this is at high metallicity. We have the same picture at lower metallicity, at the LMC, even at the SMC, even at the 10th.
Okay.
We go below 10th, at the 20th.
Then they might go
then
a little bit.
The mass size become lower. Then you don't get these optically thick winds.
Okay. That's really good.
So it's not just a Z dependence, it's a Z dependence and a gamma dependence.
Okay. And then my last kind of question / comment, you did already mention this yourself, like you were doing this for single stars for the 30 solar mass, but you lose a lot of mass for the low rotating ones, right? So in the context of gravitational waves, for the 30 solar mass peak, in the context of gravitational waves, those stars would all widen an incredible amount, right?
Yeah, so you mean this...
Yeah. So if you go from the green line, like on the right-hand side, I can see they're all rapidly rotating. It'll be fine. No, still, it's M initial still high.
You're getting the other way. The right side they do a lot of math.
Yeah, sorry. Yeah, well, on the left is still also, you go from 90 to 35.
Then you go from 90 to 80. The total mass is 80. You start at
Okay. Yes, no, you're right. You go from black to green. Okay, so the high rotating ones would probably all be too wide to merge, I guess. Does that make sense? Well, you were doing a single star.
I've been just doing a single star models here.
Okay.
Thanks. Maya Fishback. So do you know at what metallicity like that drop happens between a maximum mass of 90 and 30?
Yeah, in our models, it's just below a tenth.
Okay.
I could imagine if the mass loss rates are maybe not exactly right, that the feature that the drop could be at slightly different metallicity. But I would say the feature itself is probably more robust than the exact metallicity where it happens, because it's set by different physics. The 90 is set by different physics than this feature.
Yeah, and I guess is the low metallicity here all the way down to like 0 metallicity pop 3 stars?
We only ran to 1,000, but yeah, it should also go to.
Okay, like nothing non-linear or crazy happens when you go to pop 3.
It'll just no, it'll be the exact same. Yeah.
Cool, thanks.
Okay, we have a couple more minutes for one last question, if one is there. I mean, we're all pretty tired, I guess. So if not, let's close it here. Let's thank Jorick again. And thank to all the speakers of today. We'll see each other tomorrow.